Welcome. Here we are today with Randall Jibson, an expert on landslides from the United States Geological Survey. He's going to teach us more about landslides and earthquakes and how they impact us. And he will be taking your questions that you submitted.
Happy to be here.
Thank you. So to get started, how do we determine landslide risk?
Well, that encompasses everything we do here.
Oh, great.
And so we start with something we would call landslide susceptibility, which is we look at how steep is the slope in a given area, what kind of rock or soil is there, how strong is that rock or soil, what kind of vegetation is on the surface. Those are things that don't change much through time, and they make a slope more or less susceptible to landsliding. Then we plop on top of that what we would call a trigger, an earthquake, heavy rainfall. Maybe there's a thick accumulation of snow that melts very, very rapidly and pumps a lot of water into that slope. So if you combine how susceptible a slope is with a certain kind of trigger, that tells us how likely it is that a landslide is actually going to happen in a given area. Now, if you really want to move to the word risk, you also determine what's in the path of that landslide. Are there houses, buildings, roads, power lines? So when a landslide occurs, if it occurs out in the middle of nowhere, that's what we would call a landslide hazard. But if it hits a house, that's what we would call landslide risk.
Yes.
And so that means that it's actually going to impact something. So we have to gather a lot of data on how steep the slopes are. The hardest thing we gather is the nature of the soil and rock. What is the strength of that soil and rock? What are the groundwater conditions? All those things are very, very difficult to gather. But when we put those together, then we put together a model basically that says if we take those conditions, if we shake it with an earthquake, if we rain on it, if we do something like that, what's the probability of a landslide actually happening? And what's in the path of that landslide?
Thank you. So for you personally, for those of us who may want to become landslide experts in the future, over your career, how much time do you spend in the field gathering data versus doing numerical modeling here in the office? And has that changed from the beginning till now?
It probably has changed because of the availability nowadays of a lot of remotely sensed imagery, satellite imagery, imagery from drones, unmanned aerial vehicles. There's a lot more that can be done in the office by simply accessing and downloading digital information. When I started, well, we had airplanes with cameras.
Yeah.
And aerial photography is very, very, very important. But we had an old rule of thumb. For every day you spend in the field, you're going to spend 2 weeks in the office. And that was a reasonable ratio. But both are important. We need to go out and actually see what's happening on the ground and gather data. And we use that to calibrate the models we make and what we see on that imagery. I mean, you can look at a satellite image of something and you think, it looks like that's where the landslides are here and there. But until you've been out on the ground to see what they actually look like, you're not really sure what you're looking at.
Okay.
So there's probably a 10-to-1 ratio of sitting in the office versus one great day in the field.
Okay. Sounds good. So if I wanted to determine landslide risk for my own home, are there things that I could look for, or is this something that we have to leave to the experts?
In a big, broad sense, if you're going to go buy a home and you wanted to avoid landslides, there's some obvious things you could do. Don't
Right.
buy a house on the edge of a cliff. Don't
Right.
buy a house on the bottom of a long slope. Beyond those pretty obvious things, it really is in the realm of experts. A person who was interested in landslide hazard and risk at their own specific location would probably need to hire a certified geotechnical engineer or an engineering geologist. Those are two closely related, kind of overlapping fields, but those are the people that have that expertise. Because sometimes you might have some hazards that wouldn't be immediately obvious to a layperson.
Right.
Now, there's some areas where there are landslide country is covered by maps like that.
Okay.
It's just a few places.
Okay. Great. So you had talked about triggers for landslides. Are there any human-made triggers? Can human activity trigger landslides?
Absolutely. There are certain things that are well known and associated with landslides. Road construction in mountainous areas is one of those. You've got a mountainous slope, but if you then make a road cut in there for a road, you create an even steeper slope on the edge of that road. And so-called road cuts are areas where we can make landslide hazard worse. If we go in and put a large development in an area, we can alter the drainage, and if we don't account for the drainage patterns and characteristics, if we don't carry enough water off of a newly developed area, we can concentrate groundwater in some areas, which can make the landslide hazard worse as well. So really drainage and altering the actual geometry of a slope are the two things that humans can do that are most likely to increase landslide hazard.
Okay. And what about global warming? We've talked about climate change and how that changes precipitation patterns. Do we know yet if that is affecting landslides around the world or not?
I don't personally think we have a really good idea about that. I think if you look globally, I think it's going to be a wash, because there's some areas with a changing climate that might get more rainfall, and landslide hazard would be worse in those areas. There's other places where the models say, oh, we're going to have drought and it's going to be drier. You would have less landslide hazard in those areas. So I think if you add it all up globally, it's liable to be a toss-up, but some areas it might get worse and some it might get better. I don't think we have good models yet of specifically what climate change might do to landslide patterns.
Okay, thank you. So when these landslides happen that are man-made due to changes in slope or changes in drainage, can you tell us anything about the liability, or is that all over the place?
That's what makes lawyers rich. There's a large body of case law about this, and everybody points their fingers at everybody else. There's not one consistent rule about who's liable. It depends on, did the contractor execute the job correctly? Did the geotechnical engineer who designed it design it correctly? Did the permitting agency, the city or county, did the permitting agency correctly permit it? Were their rules appropriate? Because there have been cases of landslides where contractors have been sued, geotechnical engineers have been sued, cities, counties, and states have been sued. And in different cases, those lawsuits come out differently. So sometimes it's a matter of the deep pocket rule, who has the most money.
Yeah.
Pretty often, local government entities are sued. A city or a county who issues a permit, they're the deepest pockets. They're the ones who are around. Sometimes a developer isn't even in business anymore. And often they end up being sued, which has the net effect of causing them, over the long term, to be more conservative in how they permit things. So they will make landslide hazard zonation maps that require a lot of special studies in some areas, because they're trying to protect homeowners and landowners, but they're also trying to protect themselves against the possibility of that kind of liability.
Okay. So along those lines, are there any things that can be done to prevent landslides or to protect homes in at-risk areas?
Sure. And it depends on the kind of landslide. It's heavily dependent on the kind of landslide. For small garden variety landslides, a common type is debris flows. That's what happens when you get very heavy rainfall on a steep mountainside. It saturates the ground, and something maybe no more than a half a meter or a meter deep cuts loose, becomes a slurry that moves very quickly. It's got maybe the consistency of wet concrete, and it can come down the hill pretty fast. For landslides like that, you can build deflection walls. There are homes in Southern California, actually, that have, for example, garages with doors on both ends, and if there's debris flows about to happen. They open both of them, and it comes right through under the house. And so you can deflect those and form debris flow catchment basins and things like that. But on the other end of the spectrum, for big, deep landslides, a mountainside is moving.
Yeah.
Not much you can do. But there's everything in between. For some deeper kinds of landslides, you can do structural things. You can put a large retaining wall at the bottom of a slope. You can actually drill caissons into the slope and put reinforced concrete cages in there to try to actually pin it in place. But the earth is heavy, and people say, can you prevent that landslide? And my rule is, any landslide can be prevented if you have infinite money and resources. But when it comes to economic viability, what would it cost to actually prevent a landslide here versus the value of what's being protected? That's a difficult trade-off, and often avoidance is the best strategy. You look at that slope and you say, we cannot economically stabilize that slope. We got to put our project somewhere else.
Yeah.
So
if I saw a landslide coming towards my house, what could I do to protect myself?
like literally coming towards your house,
yeah,
you would run. Landslides happen at a full spectrum of velocities.
Okay.
There are landslides that happen so slowly they can never be seen with the naked eye. But over years or decades, they will tear a house or a building or a road gradually to pieces. It's not gonna harm anybody. It's gonna destroy your property.
Yeah.
There are other landslides like debris flows that I just mentioned that happen very rapidly, as in you cannot outrun them. There are some fantastic videos on YouTube and other places of people in cars trying to outrun debris flows that are coming down roads at them. And so in cases like that, your only option is to do whatever you can to get out of the way. You just have to flee at that point. And if there's a landslide moving toward you or your house, that is not a time to be thinking about gathering up valuables and family pictures. That is a time to save your life. You know,
yes.
Men, women, children, dogs, whatever order you want to put them in, yes. But all living things, you try to get them out of the way.
Okay. And so there's no way to like hunker down in my house like I would for an earthquake. The best solution is to get out.
For a landslide, yes.
Okay.
Absolutely. In general, with an earthquake, most structures are going to weather an earthquake okay, and you're probably safer hunkering down, under a doorway or under a table or something. But if a landslide is about to come and impact your house, you could be buried, you could be crushed, and there are very few structures that will withstand the impact of a landslide.
Okay, thank you. So can you tell us about some of the largest and worst landslides that you have studied either personally or in the literature?
Yeah, I mean, there are some really big ones out there. In historic times, something that could be documented by humans, the biggest landslide on land, not counting underwater, we may talk about that in a minute, was actually Mount St. Helens in 1980.
Oh.
This is a volcano in the Cascades, and it may be before some of your students were born, but
not all of them. We have some who remember.
some of us can remember this. I was just starting my career at the USGS. This was a volcano that was about to erupt, and so there's magma, lava pushing up from under the earth in that volcano, and it's causing that volcano to swell. And as it swells, the slopes are actually getting steeper and steeper quickly over the course of days and hours. And what actually caused the eruption was it eventually oversteepened the flanks of that volcano to the point where they became unstable, and an entire flank of that mountain slid off in the biggest landslide in history. Now that had a variety of effects. There's the landslide we have to worry about, but it also uncorked the volcano. It's like popping the cork on a bottle of root beer, and that pressure was released, and the eruption immediately, and it actually came out sideways initially because it was the flank of the volcano that came off. That landslide was almost 3 cubic kilometers in volume. And I did a little fun calculation.
Okay.
And I was trying to find something of a dimension that people could relate to. If we think of the Rose Bowl, that famous iconic football stadium in Southern California, it's huge. I've been there. It's huge and massive. The volume of that landslide could completely fill up the Rose Bowl to the rim almost 9,000 times.
Oh my gosh.
So that's pretty big.
Yeah.
You know.
Yeah.
That was a great deal of material. Interestingly, the largest landslides prehistorically that we've ever seen are 10,000 times that size.
Okay.
Like fill the Grand Canyon 5 times.
Yeah.
Really, really
Wow.
huge.
Okay.
But historically, there have been some pretty huge landslides, and some
So
of those.
was there something different about the planet historically that we haven't seen anything like that since? Or could we have one of those somewhere?
We could. I mean, the planet is always changing, and these really, really, really huge landslides, they happen rarely. And so you got to look back several million years to just catch one of them.
Right.
Conditions certainly were different then. I'm not sure we completely understand what conditions were then, but there's no reason that things like that couldn't happen now.
Okay.
And I mean, you don't like thinking about it. It's kind of like, what if the Yellowstone caldera explodes? It would take out the United States, you know. But those things in geologic time have happened and do happen, but they are rare enough, you know, if like the biggest landslide anywhere, and it's a submarine landslide, 20,000 cubic kilometers. That's the one that could fill the whole entire Grand Canyon 5 times. That happened 2.5 million years ago. A couple of landslides, not underwater, one in southern Utah, one in Wyoming. They were both 2,000 cubic kilometers, but they happened 20 million years ago, 50 million years ago. So conditions were different. Mm-hmm. I'm not sure we know exactly what the conditions were, but you can look at those and say, wow, that's interesting. The likelihood of it happening in my lifetime is low enough I'm not going to worry about it.
Yeah.
But the likelihood of something like Mount St. Helens happening is much higher. And just the landslide part of Mount St. Helens, we think of the eruption, but just the landslide, it traveled dozens of kilometers downriver and inundated towns and killed people on its own, independent of the actual eruption and ash and all that stuff.
So that was my question with landslides. Did we have any warning of that Mount St. Helens landslide? Had people been evacuated yet? Because I know people were evacuated before the eruption.
Yes. When it comes to predictions, we're pretty good at volcanic predictions because this is a massive magnet that's moving from deep in the earth upward, and using seismographs, a variety of kinds of geodetic measurements, geomagnetic, chemical, all kinds of things. Our volcano people are really good at predicting volcanoes.
Yeah.
So prior to Mount St. Helens, there was an evacuation zone. The USGS lost one scientist in that eruption, a person at a kind of a forward observation base that didn't get out in time. He volunteered to be there, but that they had been evacuated, and we have successfully evacuated people and saved thousands of lives all over the world. Mount Pinatubo in the Philippines, a number of them in South America, where our people have done a really good job of saving lives. Earthquakes and landslides are much, much more difficult to predict.
They're kind of like a warning sign for the volcano.
Yes, and sometimes we have these chains of disasters because a volcano, there are earthquakes related to a volcano, there can be landslides, as I just described, as well as the eruption itself. So we sometimes have these chained hazards that are moving along, that are all interrelated with each other. Now, we define prediction as time, magnitude, location. That's how we define that. And we're pretty good at forecasting, like, hey, this is where we think there are going to be earthquakes and landslides. This is how often we think they happen. This is how big they generally are. But in terms of saying, hey, in the next 2 days, this slope's going to fall down, or there's going to be an earthquake of this magnitude, we're not going to see that in our lifetime. Yeah. Honestly. Okay. Now, there are times we can predict landslide, catastrophic landslide release. Sometimes the slope will begin to move gradually, and then its movement will accelerate. And if there are people monitoring a slope and they can see, wow, the movement rate is going up, then we can predict with some level of certainty, hey, in the next few hours or days, something's likely to happen. Get people out of here. And that happened recently in the Nepal earthquake of 2015. There was a landslide that cracks were opening at an increasing rate, and they evacuated a village, and it cut loose, and nobody died, but there would have been dozens of fatalities had they not done that. But those are just in a few specific locations. Right. In general, it's pretty hard to do.
Okay. So we mentioned submarine landslides before, and somebody had a question about that. Can you tell us anything more about submarine landslides, how they form, how are they different than landslides on land?
Yeah, they're interesting beasts. I don't study them specifically, but I marvel at them. They are by far the biggest landslides. The largest landslides anywhere on the planet are all submarine landslides. That one that I mentioned, 20,000 cubic kilometers. That's almost tectonic. That's almost a plate moving around. Yeah. And they can move, because they're underwater, the physics are different. That landslide moved 500 miles.
Oh my gosh,
okay. And they can move.
That's like from here to Kansas City.
Yes. That's like Salt Lake to Reno, you know. Yeah. And they can move on ridiculously flat slopes. 1 degree, half a degree. Wow. A slope that if you were standing on it, I guess a scuba diver, but if it was above ground, you would say, that's as flat as Kansas, you know. So imperceptibly flat slopes. And, you know, because it's underwater, the fluid pressures are very, very high, and this material is not very stable. The two things that are most likely to trigger a submarine landslide are earthquakes, and we have records of massive submarine landslides, huge submarine landslides triggered by earthquakes. Sometimes the way we know when they're triggered, they have broken submarine telecommunications cables.
Oh, okay.
And there'll be multiple cables in different places, and it'll break this one at this time, and it'll break this one at this time, and this one, so we can get the speed of those things. And we know, hey, an earthquake happened right before those cables broke, you know. Yeah. So we've got that nailed down pretty well. So earthquakes can trigger those. Also, there's a lot of chemical reactions going on the seafloor, and so gas hydrates, so-called, just gases that are seeping out of the seafloor, they can reduce the effective stress on the soil, which basically means it just almost floats that soil off the surface and lets it go and get moving. They can also happen just spontaneously.
Okay.
And that's true of landslides everywhere. Sometimes we can say an earthquake caused that, rainfall caused that, but landslides are cutting loose all over the planet all the time with no obvious trigger. There's just a gradual change of conditions until it reaches a tipping point, and the slope is no longer stable.
Okay. So how do these submarine landslides cause tsunamis?
A tsunami is, whether it's by an earthquake or a landslide, a tsunami is caused by a displacement on the seafloor. Okay. And the analogy I like to use, you're sitting in your bathtub, and you know the water's up to here. If you took your hand and put it flat near the surface of the water, if you moved it quickly to the bottom of the bathtub. That would displace a bunch of water in the bathtub and waves would go out. And so the kinds of earthquakes that cause tsunamis are earthquakes that cause a rapid displacement of the seafloor. And that it does exactly what I just described. It displaces a bunch of water and waves go out from there. Landslides can do the same thing. If there's a submarine landslide, it rapidly displaces a large amount of seawater. In the 1964 Alaska earthquake, the earthquake itself caused a tsunami. It killed people in Northern California, the Alaska earthquake. But there were multiple submarine landslides, for example, near the city of Seward, the city of Valdez in Alaska, submarine landslides near the port that caused local tsunamis that killed dozens, hundreds of people, and totally wiped out towns from landslides that rapidly, they just displace this water and that sends these waves shooting out. You just think of that bathtub analogy, and it's not that hard to understand how it happens.
Okay, thank you. So we often hear them talk about, and you touched on this already, but being overdue for an earthquake. Is that real, or is that something that we should worry about? They say that the Pacific Northwest is overdue for a major earthquake.
Right. That word is a controversial word.
Yes.
There are scientists who quite clearly don't like the term overdue. It makes it sound like a pregnancy.
Yes.
And that it's like, wow, it's got to happen any day now. And yet there is a little bit of truth to that word, because the way we don't predict earthquakes, specific time, size, location, but we know pretty well on the planet where earthquakes tend to happen. And in many areas, like the Pacific Northwest, we have a pretty good idea of how frequently they happen and how big they are when they happen. And that whole area along Washington, Oregon, that's along a tectonic plate boundary, a subduction zone boundary. That area is called the Cascadia subduction zone. And the southern part of that zone, the Oregon part of that zone, these big earthquakes tend to happen there. I looked it up, about every 250 years or so. The last one happened in the year 1700. So we are 60 years or plus or minus past the average return period for an earthquake there. And that's one of the ways we measure overdueness.
Yeah.
How far past the average are we? But the average is just an average. If you think of a bell curve, you know, the average is the average. But some of those curves are wide and fat, and some of them we know very accurately. But these earthquakes, pretty much anywhere, sometimes they happen with a great deal of regularity, but sometimes there'll be two or three pretty close to each other, then there'll be a long period, and so we look at the average recurrence interval, but some of those have a large standard deviation. But undeniably, in the southern part of the Cascadia subduction zone, we are overdue. If you want to use that word, we're about 60, 70 years past the average time. Now, it's interesting, in the northern part of that area, maybe up in northern Washington and those areas, we're still shy of the average. Up there, they tend to happen about every 500 years, and we're only 300 years in. So we,
200 years of sleeping easy.
Except half the data is on the front half of that curve, and half of it's on the back half. Another area of interest is along the Wasatch Fault Zone in Utah. The studies that have been done there, they measure overdueness in how many times past the average are we. And so, for example, the Brigham City segment it's 2.5 times. It's been 2.5 times the normal period between earthquakes since the last one. That sounds overdue. The Salt Lake City segment is 1.5 times past its normal recurrence interval. So those are two areas where we could properly say they're overdue, but that doesn't mean it's imminent. In the Cascadia subduction zone, the probability study showed that there's about a 1 in 3 chance of a major earthquake there in the next 50 years, which is a pretty big probability. but it's not like I'm packing my bags and leaving because it's happening tomorrow. So
Right.
you kind of have to weigh that.
Yeah. Okay. So sometimes we hear people that seem a little bit melodramatic and talk about how California is going to fall into the ocean and be no more, and
Yeah.
and apparently they've been saying that about the Pacific Northwest also. What do you think the probability is that California is going to be gone in the next century?
There's no place for it to fall.
Okay.
Is what I like to say. If you were an honest scientist and if you drew a cross section from way offshore
Hmm.
of the seafloor and then the coastline and then up over the Sierra Nevadas and everything. One of my first geology professors did this for us to give us perspective. You can't even see the Sierra Nevada in California. Like, where is it? Oh, that little point right there. Uh, the surface of the Earth, from a planetary global perspective, is relatively flat.
Yes.
Okay, so the Earth is 24,000 miles in circumference, and the highest mountain is 5.5 miles above sea level. As a proportion of 24,000 miles circumference, it's nothing.
Yeah.
And so if you actually looked at it, there's no place for California to fall or to slide or to go. Now, it might be torn in half.
Yes.
It is being torn in half, California. It might be shaken to pieces, but it's not going to go anywhere in terms of falling or disappearing or being submerged. It's a fantastic Hollywood plotline,
Okay.
but not a physical reality.
Okay. And the same goes for Washington and Oregon. We
Absolutely.
can sleep sound that they're going to be there for a long time,
Yeah.
if
Now-
not there somewhere.
Hey, there's going to be some cliffs that collapse and fall in the water,
Right.
but in terms of large pieces of states vanishing, that's fantasy.
Okay. Good to know. And then our last question is about the New Madrid Fault in Missouri.
Yes.
Has that had any activity recently, or has it been quiet since the 1800s?
Well, it's had ongoing activity since the great events of 1811 and 12. You're in my wheelhouse now. That's
Okay.
where I did my PhD dissertation. But it has had, since the 1811 and 12 events, where there were at least 4 in the magnitude 7.5 range. If those happen now, it would be a national catastrophe. Literally.
Yeah.
It would wipe out our economy. But since then, there have been a couple of 6s. There have been several in the 5 range and lots in the 2, 3, 4 range. So there's ongoing seismicity there. That's a seismic zone that isn't along a plate boundary,
Right.
so we don't understand it as well. It appears that the return period for really big earthquakes there is about 500 years, and we're about 200 years in. But we just don't know that much. It's not as well studied, and the very reason why earthquakes happen there is not as well understood.
Okay.
And the physics of the fault movement, since it's not on a plate boundary, is not as well understood. But there is ongoing seismicity there. The problem in the mid-continent is the crust is different there.
Okay.
Out on the plate boundaries, California, the crust is younger, it is warmer, it is less dense, it's all cracked up and fractured up, and so the seismic waves, they don't travel very efficiently. They're scattered and energy is absorbed. But in the middle of the continent, the crust is what we call old and cold. Okay? It is solid, it's not very fractured up, and the earthquake waves
Travel
take
forever.
off and go.
Yeah.
And so for exactly the same size earthquake in the mid-continent versus California, for example, the area affected at the same level of shaking will be 15 to 20 times greater in the mid-continent.
Wow.
So a magnitude 6 in California would do moderate damage.
Mm-hmm.
A magnitude 6 in the mid-continent would be catastrophic. There's a lot of old brick structures that would fall down, and it would encompass a dozen states, where in California it would be a local regional event.
Right.
And so that's a trade-off in earthquake risk in the mid-continent, is the earthquakes are smaller and less frequent, but they affect a much, much larger area.
Okay. So we studied some of these earthquakes, and some of them are not at the plate boundary, but they're close to the plate boundary.
Mm-hmm.
Is the New Madrid seismic zone a little bit unique in being like so far from any plate boundary?
Yeah, there's a family of earthquake zones that are these mid-plate zones, and there's some of them all over the world, and so it is very different for that reason. Structurally, it's a place that tried to become a plate boundary but failed.
Okay. Okay.
So you got to feel sorry for it.
Yeah.
It really, really tried, but it
Yeah.
failed. And I don't want to get into a lot of terminology,
Yes.
but because of that, there are cracks and imperfections in the crust that
Okay.
run up the Mississippi Valley. That's why the Mississippi River is there.
Okay.
It was more erodible in that area. And if you think of a plate, we think of a plate as being this rigid thing, but there's other plates sliding past it all along the edges. That's going to stress the whole plate.
Right.
And in the interior of a plate, those stresses have to be accommodated somewhere. They're going to be accommodated at the weakest places. And in that case, it's a fracture zone that tried to be a plate boundary and failed, and so that's where the stresses are likely to be accommodated in the interior of a plate. And we've seen these in India. There's people who spend their whole lives studying what we call intra-plate earthquakes, not on the boundary.
Okay. Well, I think that is all of our questions. Is there anything else you think that we should know about landslides or earthquakes that you haven't covered yet?
They do a lot of damage. We talked for a few minutes about some of the biggest landslides, but those weren't necessarily the most deadly landslides. Worldwide, landslides take thousands of lives every year. The most deadly landslide we know of was in an earthquake in China in 1920. It caused hundreds of landslides in a soil called loess, which is it collapses during earthquake shaking. Killed 100,000 people. The landslides.
I think that's one of our case studies next week that they'll be studying, and it was my understanding that it killed around 100,000 just from the landslides.
Yes.
And then there were many more who died due to changing the riverways and.
Yeah, there's flooding and there's buildings that collapse.
Yeah.
Poorly constructed buildings. A well-known landslide in 1970 in Peru. There was a magnitude 7.9 earthquake. It caused a big, massive ice and rock from the tallest mountain in Peru, Nevada, Huascaran. It collapsed and fell vertically about a kilometer vertically. And there's these mountain towns kind of up against this cliff.
Yeah.
That mass hit the ground and took off, and it was traveling at about 200 kilometers per hour. It went 16, 17 kilometers, completely buried two cities. They ceased to exist, and perhaps 20,000 people were killed. And so there are certain environments where these things can be unbelievably devastating when they happen. We're lucky in the continental U.S., the 48. We don't have the same kind of geography that might create that sort of hazard, but we do have places, the Wasatch Front, Southern California, all along the West Coast, where landslides can have devastating effect both on property and on human life as well.
Okay, thank you. Well, thank you so much for meeting with us today. Thank you, class, for participating, and we'll end it here. Thanks.
Okay.